Hello everyone. In this video I'll show you how to simulate the basic series as well as parallel DC circuits along with the simulation of rectifier circuits. So let's start simulating a basic series circuit using a software tool called as Multisim. So for that again you go for place component. In this component I'll place a source, that is under the power source you'll be having something called as DC power. I'll place it over here. Then I have to place different values of a resistor. So again under the group I'll go for basic. In the basic I'm having a lot of components. Under that I'll select any one value of resistor. Let me say that I'll take 1 kilo ohm. Then again I place one more resistor over here. Let me say I'm placing three values of resistors over here. I can change the value of resistors by double clicking on the value of the resistor. Then I can change it to 2 kilo ohm. Then I'll change it to 3 kilo ohm. So if it is kilo you have to write it as K. Then you have to connect all the resistors with the source. Now once you connect, I have to see the voltage drop across each of the resistors. To see the voltage drop across each of the resistors, in the laboratory experiments we normally use multimeter. The same multimeter is available towards the right hand side of this window. So the first option is multimeter. You can click on it and you can place it over here, which is XMM1, which gives you the voltage drop across the first resistor. Now the same I'll copy for the second, copy and paste for the second one and for the third one. Now when you double click this, you can see that XMM1, you can have XMM2 and you can have XMM3. Now if it is an AC voltage, you can get the AC voltage, current, amperes, ohm, equivalent value of resistor. Now you can see that I have to calculate what is the voltage drop. Your 12 volts what you supply, the energy has to be transferred somewhere. It can neither be created nor be destroyed. So it has to be transferred from one place to another place. So this 12 volts gets distributed across 1 kilo ohm, gets dissipated across 1 kilo ohm, 2 kilo ohm and 3 kilo ohm respectively. So let us start simulating this circuit. So once we simulate, we can see that it is 2 volt which is a drop which is occurring across 1 kilo ohm, 4 volt which is a drop which is appearing across 2 kilo ohm, and 6 volt that is a drop which is occurring across 3 kilo ohm resistor. So 2 plus 4 plus 6, which gives you a total supply voltage that is equal to 12. Now if you are calculating the main current or the supply current, theoretically it is series. The equivalent value of this resistor is 1 plus 2 plus 3, which gives you 6 kilo ohm. So supply voltage according to Ohm's law, it is 12 divided by 6, which is nothing but 2 milliamperes. So let us verify by connecting one more multimeter over here, which gives you the supply current. So as you know that the ammeters are always connected in series, I'll connect it something like this. So the current will flow through the ammeter through the resistors. So now when I double click this, XMM4 will give you the current over here, but you need to change from V to A, which is nothing but the current, and this is DC. Now let us run this and you can see that simulation error has occurred. So let us see what is the error. 12 is connected to XMM4. It's a voltage. Connect multimeter. And you can see that there is a 2 milliamperes current which is flowing through the circuit. So this is how you simulate a series circuit. Now let us go for simulating parallel circuit. So again you create a new window for the next design. So I can copy the same source to the next window. It's not compulsory that again you have to go for placing the components, separate components. I can place the resistors. I can copy paste this resistor over here. Then again I'll place this over here. Then I connect the values over here. Now in the parallel circuit, as you know that the voltage drop across the resistors are same, which means that the voltage drop across R1 and the voltage drop across R2 should be same as your supply voltage, because both the resistors are connected across a 12 volt supply. You can measure by using a multimeter again over here. When you run this, you can see that it is 12 volt, which is nothing but the same as supply voltage. As you know that in a parallel circuit, the current gets split up across the branches. Let us have three multimeters which shows the current across two different branches and one for main current. So I am having two multimeters and have to rearrange because ammeters are connected in series. I'll place one ammeter over here, one more ammeter here across the second resistor, then supply current. Now I have to keep it in ampere, set to ampere. Now let us start simulating this parallel circuit. You can see over here the main current is a 16 milliamp and the branch current across 1 kilo ohm it is 12, and across 3 kilo ohm it is 4 milliamp. So 12 plus 4 giving the main current as 16 milliamps of current. So you can verify with the theoretical calculations, you'll get the same value. So this is how you simulate series as well as parallel circuits. So now let us go for simulating rectifier circuits. So the basic rectifier circuit is a half wave rectifier, which is also called as series flipper, because it is flipping the negative portion of your AC signal. So let us start simulating this. So again we'll go for placing the source, because it is a sinusoidal voltage what you are placing. So in the power source, I'll place a AC voltage source over here. You can also place a transformer. I'll be describing how to place a transformer in a full wave rectifier circuit. So I'll go for AC signal, then I have to have a diode. So in this under group you are having diode. So you can select a diode. Normally we select 1N4001 diode. So it's not compulsory that you have to use the same diode again. Then I should have a load. So I connect a resistor. So it's a 1 kilo ohm resistor what I connect over here. So connect it to the resistor and over here. Now if you want to change the voltage of the supply voltage, double click on the component. You can change the RMS value of voltage. I give as 10 volt RMS value and frequency I'll set it as 50 Hertz. Then press OK. So it will be changed over here and there is no phase. Next over here the load 1 kilo ohm, let it be as it is. Now I have to see the output waveform as well as the input waveform over here. You can see that for a positive half cycle the diode D1 is forward bias, so the full complete positive signal will be appearing across the load, and for the negative half cycle the diode is reverse bias, which means that the switch is open, so there will be no voltage appearing across the load other than the voltage drop of the diode. Since it is an ideal diode what I have considered, so the voltage drop will get it as 0. So it's an open switch for the negative half cycle. So on the right hand side you are having a different oscilloscopes. Over here I am having oscilloscope which is of 2 channel. I can place it over here. or else I can also have something called as Tetronics oscilloscope, which you can see even in your laboratories. So when you double click this, you will get the similar Tetronics oscilloscope what you find in our laboratories. So right now I'll be using a 2-channel oscilloscope. You are also having 4-channel oscilloscope in this measuring instruments. I'll discuss about this later. So here in this 2-channel oscilloscope, I'll connect one for the input and one for the output. And one for the output. So let's simulate this. Okay, I have not given the ground, so I'll give a ground over here, ground, and I place it over here. Now let's start simulating this circuit. Double click this, you can see that you are having a running waveform. You can stop this by stop, and you can drag it, and you can see the input as well as output. Since the colors are same, it is slightly difficult for us to identify which is the input and which is the output. So you can change the segment color and then you can run. Since this wire is connected to the output, I can change the segment color of this output. You select this wire which is connected to the output, then right click on this and you can change the segment color. And you change the segment color to something blue or any color of your wish, then run. When you run this, you can see a running waveform. Stop this. Now you can see the input as well as the output waveform. It's a series negative flipper. Now how do you measure what is a time, what is a frequency, or what is a magnitude, and so on? So you are having something, you can change the scale over here. So by changing the scale, even the output waveform gets varied. So I keep it as 5 volt per division for our convenience. Again, for the channel B, I keep it as same. Now over here, channel A, I have connected it to input. So red color, what is indicating is channel A, and the blue color, what is there, which is nothing but the output, which is channel B. Now channel A is AC, and this is a pulsating DC what I'm going to get. Now if I want to see what is the voltage across any point of time, I'm having a line, green color line over here. Now you can also view this by having a reverse, by pressing reverse button, which changes the background color to white. Now there are two lines over here, for 1 and 2, which is mentioned over here. One is a trace 1 and the second one is a trace 2. Now I can check the trace over here. See, you can see the trace over here, and it is tracing the channel B. And you can also measure what is exact magnitude, that is a trace 2. When I'm moving this, you can see that the trace T2 is keeping on changing. See the maximum voltage over here. In the trace 2, the point is going to the maximum. T2, the maximum voltage is 13.99, or it is slightly 14. You can see that it is a 14 volt in the channel A and 13.406 in the channel B, which means that the input voltage is 14 volts and the output is 13.406. A slight variation in the voltage because of the load resistor of which is kept as 1 kilo ohm. Next, you can see that the voltage what I have applied over here is 10 volt RMS voltage, but the voltage what you are getting over here is V peak or VM. VM, you know that for a sinusoidal signal it is Vrms into root 2, because we are having the formula Vrms as Vm divided by root 2. So when you multiply 10 into root 2, you are going to get as 14 volts. So the peak voltage V peak to peak is 28 volts. So this is how you simulate this rectifier circuit or a clipper. Then let me say that you want to remove this pulsating. I can again give a capacitor over here, a capacitor value of any value I can give. Let me say that I will give of 20 microfarad capacitor. I connect it across the output. If you want to rotate, just press Ctrl R to rotate this and press close. Then I'll connect this at the output stage. Then again I run. You can see that there are ripples. at the output stage. It's a pulsating DC, but there are ripples, but the ripple component is more over here, so I have to reduce this. So if I have to reduce this, the procedure is I have to increase the filter capacitance value. So instead of 20, I give as around 100. So you can, when I give 100, you can see that the ripple content will be less. Now if you want to make it still lesser, then again I have to increase the capacitor value and give it as 1000 microfarad, and again I'll run. So you can see that the ripple content is very less now, and it is almost equivalent to a DC voltage. So this is how we simulate this half wave rectifier circuit. Next we'll go for simulating full wave rectifier circuit. So I have to have a diode, two diodes which has to be placed. So again I'll place two diodes, and I can copy the resistor from the previous design, the components which are required, and again I have to place a center tap transformer for a full wave rectifier. So again I go for place component, and in this I can go for all groups. Under this I can find out something called as transformer. Under the basic we can find there is something called as transformer. I should have a center tap transformer right now, so I'll select one primary, one secondary. There are many options which are available, 1P 4S, in the sense it is one primary, four secondary. Now I have one primary and one secondary, but it is center tap. I place it over here, then I have to place a source, and I place a source over here as a AC signal. I place it over here, so I'll connect it here, and again I give 10 volts, and it is 50 hertz. Then I connect the diode to a resistor, sorry, I connect the two diodes, then it has to come through resistor, and it has to be connected to the center tap transformer. Then I have to connect it to ground, so I have to place a DC ground, towards the center tap. Now let us again place an oscilloscope over here, a two channel oscilloscope. Channel A is input and channel B is output. I have to change the segment color. I'll change the segment color to blue. Now let us start simulating. Now you can see that it's a center tap transformer of the ratio 10 is to 5 is to 5, which means that the number of turns in the primary is 10, secondary is divided equally as 5 and 5. So if you want to change, double click on the component, again you can change the values anywhere over here. I can change the values, press OK, then click on run. Then over here you can see that it's a full wave rectifier circuit. I'll stop this, and if you can see that it's a full wave rectifier circuit where the output is present for both positive as well as negative half cycle. The main advantage over half wave rectifier is that the negative portion is clipped in a half wave rectifier for the negative half cycle. For a negative half cycle it's clipped, and in full wave rectifier the diode will be, the other diode will be conducting for a negative half cycle, D2 will be conducting. So this is advantage of using full wave rectifier over half wave rectifier circuit. But there is a main disadvantage in the case of this rectifier, because in the center tap the complete secondary of the transformer is not utilized at a time. Let me say that for when I am applying a positive half cycle over here, only the first half portion of the transformer is getting utilized. In other words, diode D1 will be conducting, the current will flow through the diode, through the load, and through the center tap and back to the supply. So this is what is happening in center tap transformer full wave rectifier. So the other alternative is going for that, which means that the transformer utilization factor is very less in the case of full wave rectifier using center tap. Now the alternative is going for a bridge rectifier circuit. So that is what we have learned. So let us start simulating this bridge rectifier circuit. I'll go for a bridge rectifier circuit. Over here again I can have, instead of a center tap transformer, directly I will give a supply. So I won't go for a center tap transformer over here, and instead of building all the 4 diodes again from the scratch, I can directly have a 4 diode set which is already present under diode of the diode component. Over here something we can see FWB. FWB is a full wave bridge rectifier circuit, and I can directly place the diode set over here. Then I can get the load, that is 1 kilo ohm from this set, and I connect the supply over here. Then I have to place a ground, and I have to place a oscilloscope over here. If you want, I can also place a Tetronics oscilloscope. In the Tetronics oscilloscope, it's a 4-channel oscilloscope. For the first one, I'll give it as input. I'll give auto set. Over here, the difference. You can see that once again a change. Instead of this, I'll place a simple 2-channel oscilloscope. Then I place at the output stage, and I change the segment color over here again to blue. I press OK. Now you can see the output waveform. Again, it's a full wave rectifier circuit. You can see without a center tap transformer. The same waveform, the waveforms for both full wave rectifier as well as the bridge rectifiers are same, but the only difference is the transformer utilization ratio. There, the transformer utilization ratio is very less. Over here, instead of this transformer, we are using the 4 diodes. You can see that for this diode set, during the positive half cycle diode D1, the current will flow through the diode D1 through the load, then through this diode which is there in the diagonal position back to the supply, and during negative half cycle the current will flow through the diode D3 and back over here, and through diode D4 which is in the diagonal will go back to the supply. So this is how you are simulating a full wave rectifier circuit. Again, I can have a capacitor filter which can be connected across the load over here. I connect it across the load, and again I simulate this. You can see that the ripples are very less. Instead of pulsating DC, I'm getting almost a pure DC waveform, but there are some ripples. The percentage ripple should be less based on the filter design. Thank you for watching this video. If you like this video, please subscribe to my channel. Thank you.